Imagine you're collaborating on a project board. You finish your assignment, check the box, and the status flips to complete. But your coworker, looking at the exact same task on their laptop, still sees it marked as pending. Most users assume this is a failure of the application, a bug that prevented their data from saving correctly. Today, engineers at companies like Amazon and Netflix intentionally build their infrastructure to permit these brief gaps in synchronization. The pursuit of instant truth everywhere creates significant risks for large-scale software. In these environments, seeing a slight delay in data often indicates that the system is prioritizing its own availability over absolute immediate accuracy. A simple startup app might run on a single server, talking to one database. But as the user base grows, that architecture must expand across hundreds of independent machines. This is a distributed system, an environment where multiple services and external APIs communicate across a network to complete a single task. Once a system relies on these network calls, physical limitations become unavoidable. Data packets take time to travel, and connections can drop without warning. Because information must physically travel through fiber optic cables to reach servers around the globe, synchronization is bound by the laws of physics. This diagram tracks the journey of a single update. When you change a task status, that request hits the primary database first, which registers the new state immediately. The primary database then broadcasts this update to secondary caches. This step ensures that the next time a user requests the data, it loads from a local source as quickly as possible. Simultaneously, the data travels to search indexes and analytics warehouses. These systems involve more complex processing, which means they receive the information later than the central core. This mechanical delay creates a brief window where the primary database holds the new truth, while the outer systems still hold the old record. This physical propagation of data explains why two users can see different versions of the same task for a few seconds. Architects could choose strong consistency, an alternative where every component must hold the exact same data before a user receives a confirmation. This approach requires locking the primary database, preventing any other information from being written during the update. It also requires locking every cache and index in the network until the new data is confirmed everywhere. It is the digital equivalent of making an entire stadium of people whisper the same sentence at the exact same millisecond before anyone is allowed to move. The result is a system that is incredibly slow, expensive to maintain, and prone to collapsing under heavy traffic. Prioritizing perfect, instant accuracy everywhere inevitably compromises the speed and availability of the entire platform. Professional system design resolves this through a compromise called eventual consistency. The system accepts temporary mismatches between its parts, relying on the guarantee that all components will align over time. Architects choose to trade absolute consistency for the ability to scale to millions of users while maintaining high performance. If various parts of a system disagree on the current state of a task, the software needs a way to resolve the conflict. Engineers handle this by defining a single source of truth. The primary database serves as the authoritative record, while all other components, like caches and search indexes, are treated as temporary, derived views used to improve speed. Establishing clear ownership ensures that temporary inconsistencies in these secondary systems remain manageable trade-offs for performance. Senior developers design interfaces that accommodate this lag, using processing states and background updates to ensure the user is never blocked by a slow network. In contrast, code that assumes updates are always instant often fails when it encounters the latency of a real-world distributed network. Building for scale requires moving away from the expectation of perfect synchronization and designing infrastructure that accommodates unreliability as a standard condition. But if we accept that networks fail and data falls out of sync, we face a new problem. If a request drops halfway through, how do you retry that action without creating duplicate records or double payments? We'll explore retry storms and idempotency